Thanks, everyone. Thanks for the invitation, everyone. Indeed, I'm really glad to be here after many years. It's nice to see PFL and how it changed over the years. So today, I'm going to talk about can neural nets learn to reason. Um, and this is joint work with a few colleagues, Chinyan, Maitra, and John. And let me start. You know, it's now 2022. We've had a tremendous many, I would say, decade now, 1 decade of successes of deep learning. And you've seen how deep learning has changed computer vision, speech recognition, natural language processing, and so many more. You've heard many of that in the previous talks, and you're going to hear even more later. All of that is great, and it has a lot of impact on society in general. And at the heart of that revolution, I would say, is the concept of generalization. So what is generalization, and what do we know about generalization? You know, in fact, we understand it in quite a restricted way, what we understand about generalization. And in fact, that restricted way is questioned by how deep learning has been successful in the past few years. So let's dive in a bit what I mean by that. So what is generalization? What do we mean? Usually the starting point of any machine learning process is we start from getting some data. We have a training set of examples, and we're going to train a model on that training set of examples. But that's only the first part. What we really want is to use that model that we've trained on new examples. And we don't really care about the training examples themselves. We want to be able to be good at new examples. The unseen set or the test set, depending on how you call it, that's usually what we call the generalization part. But can we be more precise about what that process means? Well, usually we start from a statistical definition of generalization. So what we are going to assume is that this training set that we started from actually was coming from a distribution of examples. We don't know what is that distribution. We just know that we are going to hope that the training set that we have comes from that distribution. And more importantly, when we are going to use the model we've trained on that training set, it will be used on examples that also come from that same distribution. So we don't need to know the distribution, but we need to assume that both the training set and the unseen set come from the same distribution. And it's actually quite a strong assumption, because if you think about it, in the more real-life, realistic scenario, this is basically never the case. In general, you start from a problem you want to solve. You want to, I don't know, recognize the people in photos or objects in photos, and you gather data to try to do that. But it's almost impossible to think that the data you are going to gather actually corresponds to how you are going to use it in the real life, because real life is noisy, it's complicated, it's moving along, so the distribution would shift over time. All of that makes this assumption quite too strong and actually not realistic. So we say that generalization is actually working as long as you're assuming this IID assumption that your data is coming independently and identically distributed from a distribution. Is that really enough? Well, not really. Most of the cases, will not correspond to that. So if you look, for instance, you've trained your model on photos of chairs, like here I'm showing on the top left. It's unlikely that it's going to work on some chairs that you haven't thought about, like this weird chair you can see on the top right here. So we're just hoping that the data comes from the same distribution, but it's not going to be the case. So let's try to understand the many cases of generalization that we should be able to, we would like our model to be good. First, there's the usual case, which is the IID assumption. So the data comes from the same distribution. And even more simple, which is maybe what we were doing even before, like the classical machine learning approaches, it's memorization. you hope that the data you are going to see is actually the same as the data you already saw. So this, we think we know how to handle these two cases. But there's more cases that we'd like our model to be good at. One of them is what we call out-of-domain generalization. And here we are going to see images or photos of the same objects here, chairs, but they are going to be seen in a different way. For instance, the chairs are going to be upside down, while all the chairs you've seen so far were standing up. Or there are going to be drawings of chairs. And of course, we humans don't make too much of us of that. We are generalizing over all these things, but it's maybe unlikely that our models will work on these. And then there's even more. It's when you think about the chair a bit like Melanie was saying at the beginning of the session. When you think of the chair as a concept, what does a chair do? It lets humans sit on them. And so you have examples here of chairs on the bottom right that are chairs, but they really don't look like the chairs we use for training. So this is like the worst case scenario. And you really need to think that for a model to succeed on that, it has understood the reason why a chair was built in the first place. So the question is, where are we now? What are our models able to do? What kind of generalization do they actually perform? So we talked about memorization as the first thing that we want to have. And in fact, memorization is like an important part of the story. There are a few papers in the past few years, but many more before, in fact, that showed how memorization helps generalization. One of the examples that we can see here is a paper from NeurIPS 2020. We see image. There are images from ImageNet, actually. We can see on the bottom left an image of a bassoon that is from the training set. And you can see that this image of a bassoon is not your typical image of the musical instrument, because you also see this human face in the back of it. And on the bottom right, we see test images, so images coming from the test set. And you can see a score for each of these images of how likely that the image is coming from a bassoon. And you can see that the image in the test set that is very, very similar from the image in the train set gets a very high score. So did the model actually understood what was a bassoon, or did it just saw like it's the same image, so it must be the same category? It's likely to be the second one. So memorization in that case helped a lot. And again, there are many. I see the generalization as a spectrum, and we can go from naive memorization to remembering rare examples, to doing a kind of k-nearest neighbor. Let's look at images that look like the ones in the train set, to the IID case that we understand theoretically, and then to the out-of-domain, and finally more abstract reasoning case. And that's not like a pure boundaries. It's really a spectrum. And typically we'd like to know where our models are going to stand. And are there models that are better in one cases than others? Are there problems that are better suited for that? What are the limits that our models are able to do today? It's not that clear. And so for that purpose, we've built actually a family of artificial tasks to try to disentangle all of that and try to understand where do we stand today. So we've thought of a family of tasks where we will have different kind of input. In this presentation, we are thinking just for now as images or vector. We're going to be able to control the difficulty of the task, and I'll show you an example of that. But all of them have the same overall concept. It's this pointer value reasoning approach where in the input somewhere there is a part of the input that will be used as a pointer. And that pointer points to another part of the input. And in that other part, there's the key that should tell you how to reason about the output. So you need to first understand that there's a pointer, find the pointer, get to the other part of the input, look at what there is, decode, and output the solution. So that's the overall mechanism. You can see that in multiple forms. Here I give two examples, the block style on the left and the sequential style on the right. I'll give examples of a few of them so we understand how that works. Let's look at the block style version. So in the block style here we have an image, and that image is made of 4 parts, and each part actually contains a digit, a handwritten digit. And you can see here, like 3 of the digits are described: top right, bottom left. And the top left is actually the pointer. So in order to decode what's that image, you first need to look at the top left. You should understand what you see. You see a 6, and now 6 should be decoded. And if you were to see a number between 0 and 3, you should look at the top right and decode what you see. If you see a number between 4 and 6, you should look at the bottom left, and between 7 and 9, you should look at the bottom right. So here we see a 6, so we should look at the bottom left, and what we see in the bottom left is a 9. So the target, the label, is a 9. So that's how we should understand the task for this part of the talk. Now, here there was like computer vision and decoding happening at the same time. You need to understand pointer things, and also then understand that there's a number written, a handwritten number, and then decode it. We can decompose this and only look at just numbers. Forget about vision. But it's going to be actually the same task. We are going to assume that there is a pointer. Here it's on the left. The first number is a pointer, and that says you should go to the right 3 boxes with a 0 start, so it goes actually 4. You see the number and you output it. So that's the starting point. Now we are going to be able to vary the task and the complexity of the task in various ways. Some values will appear only in some part of the image, and that we are going to call that the holdout shift. I'll give examples. Or sometimes we're going to make the decoding part more complex, and I'll give example as well. So let's look at the first simple setting. You are given this block style image, and you're going to train your model on images like this, and then test your model on the same kind of images. And that's what we call the IID case. So in the IID case, all digits can appear in all positions. So you can see any number anywhere on the 4 positions of the image. That's the usual case. But in the holdout shift setting, some numbers will only appear in some positions. So for instance, if you look at the top left, you will only see during training numbers from 4 to 9. You will not see 0, 1, 2, 3. And similarly, on the bottom left, you will only see numbers 0 to 3 and 7 to 9. And you get the point. So each position sees a different subset of the numbers. And of course, at test time, we're going to see the other numbers. So on the top right, for instance, we're only going to see 0, 1, 2, 3, while during training we saw 4, 5, 6, 7, 8, 9. So what is going to happen when we do that? Well, we can train your favorite neural net and see what happens. Here we train actually 2 models just to see whether there would be a difference. This is the IID case. So here we train with all possible combinations of numbers, and we test on the same set of combinations of numbers. And what you see on the 2 graphs is the overall accuracy. So the higher the better over time. So you see the x-axis is just training time, and y-axis is the test accuracy. And as expected, it works well. But what happens now when we train on this holdout shift setting, where the test set and the train set are different in distribution? It's terrible. Here, clearly, the test error or the test accuracy goes down and stays to basically nothing. So it's not able to recognize any of the images. Now, remember that, of course, we've changed the test sets so that we thought the task would be difficult. It's actually very difficult, as you can see here. So if we try to understand what is actually happening, we can look at a few examples and look at the output value of the model to see what the model did so that we understand what happened. So here, let's look first at the image on the right. And what we see on the x-axis is the output class. So what's the number that the model actually suggested to do, or what's the logit that each output gave. The color of the points are 3 different examples. So let's track the example, the green example. And what we see is the green example had 4 numbers, 0, 5, 1, 2. So the first number is the pointer, and it says it's a 0, and so you should actually output the value of the second number, which is 5, and that's what it's doing. So you see the green indeed has the highest value in the 5th position, so it's working well. It's doing exactly what we want. It would be the same for the other colors. I'm not going to go into that. But now let's look at the holdout shift position, which I think is more interesting. And let's look again at the green. So the green input example is 0, 1, 6, 9. So again, 0 means we should output the value of the second position, which is a 1. But you can look at the 1, and it's a very low value. It's actually outputting a 4 and a bit of a 5, but mostly a 4. And why does it do that? Because it never outputted a 1. It never saw a 1 in this position during training. So the value by default are going to be low, no matter what the input was. So it did learn something. It learned, for instance, to never output a 1 in this position when the first number was 0. But it's not the rule that we wanted, of course. So is this memorization? Is this reasoning? It's not clear what it is. And what we'd like really is to try to be able to distinguish whether we're doing memorization or the actual thing that we really wanted to understand, which was, in that case, reasoning. So what we're going to do now is try to increase the task difficulty to see what happens when the output function is different. So let's look at an example here in the vector version now. So no computer vision here, just numbers. We saw this version here. What we can do is make the task slightly more complicated by saying, well, you have to look at position number 3, so it should be a 2, but the function to decode now is not going to be just the number that you see, but the numbers in some neighborhood of that one. And here the example is a neighborhood of size 6. So you should look at the 6 values around, 2 on the left, 3 on the right, and do some kind of function about them. You can think of many functions that we can look at. Here, the function that we used was mod sum. So we sum the values of this window, and we make mod 10 on it, and we get the value that we're supposed to output. So here in this example, it should be 0 plus 2 plus 2 plus 3 plus 7 plus 9, which when you mod it by 10, you get 3. So that's the target. We could think of other functions for this aggregation, majority, min, max, median, and that there will be differences. So we're going to look at that to see what happens. So here is one graph of example to look at. So what do we see here? On the top graphs, we see training accuracy. On the bottom one, we see test accuracy. Accuracy should be high when it works. For each graph, the x-axis is the number of training examples by power of 10. So the more training example you have, the task will be more difficult to train, but maybe easier to test, and that's what we're going to observe. And then finally, between the panels on the first, the second, the third, and the fourth, it's the number of neighbors in your function. So as the number of neighbors in your function grows, it's more and more difficult to solve the task. And that's what we are going to observe. What we see here, when the number of neighbors is 0, it was the basic task. If you just look at what's the number and you output it. And it says that as the when the training set size grows, at some point, it's able to solve the task. When you increase the neighborhood size, well, you need more train examples so that the test that it works on test examples. At some point, unfortunately, when the neighborhood size is large enough, there's not enough training example to solve it in any case, and that's the first problem. Then what we look at is there a difference with any of the aggregation functions that we use? So the one I showed you was the mod sum, but we tried median, min, max, majority. And what we see, in fact, is that one of them is much more difficult than the other, and it's the mod sum. So all these functions, as the number of neighbors grow, the problem becomes much harder. You can see it. They all go down at some point. But when you have a large training set, large enough to encompass more examples, it's working for most of the aggregation function, but not for mod sum. At some point, it collapses as well. So that's a problem. In order to understand what's going on, we looked at this problem in terms of noise sensitivity of Boolean functions. So we wanted to understand how complex the task we had was. So intuitively, this noise sensitivity idea measures how sensitive the outcome of a function is by what happens when you flip some of the input bits with some probability delta for each of them. So as delta grows, you are going to have a higher probability of flipping inputs. And the question is, when you do flip that, is the output of the function different? And that's what we look. So if the function is robust, is insensitive to these flips, the value of the function will remain the same. But if it's sensitive to this flip, the value of the function will change. And that's what we observe. So what we see here is that indeed, as the probability of flipping a bit grows, the function is more and more sensitive, but it's even more sensitive as the size of the neighborhood grows as well. On the right graph, we see that it really depends on the function itself, and mostly this mod sum is by far much more difficult to understand than any of the other ones. And in fact, some of them get easier and easier, like max and min. Let's look now at another things that we could do. What if we were to vary the architecture? You know, deep learning means a lot of things. It could be neural nets, bigger neural nets. It could be transformers. These are really working well. It could be another class of models. We tried MLP mixers, which are another smart way to use high-capacity models. And what we wanted to see is if this kind of problem appeared in the same way independent of the architecture. And what we see here indeed is that there are some differences. Transformers and MLP mixers are more robust than your typical MLP. But at some point, none of these architectures are able to solve the task because it's too difficult. And we even increase the size of the training set to 10 to the large number. And even in that case, at some point, you are not able to solve the task. So we'd like to understand what kind of architecture would let us solve that task. We also changed the task in another way. And again, this is the idea of a reasoning. You remember when we use the function mod sum, because we do a sum, the order of the values should not matter. So if in the window that we see three numbers, whether you see 2, 3, 4, or 4, 3, 2, should be the same because you're going to sum them and then apply mod. But what we observe in practice is unfortunately not the case. We trained a few models where we hold out some combination of these three numbers, for instance. And what we see is that indeed you need much more example to be able to solve the task. So clearly it didn't understand really the mod sum because it was not robust to permutation of the numbers that we saw. So I'm gonna skip because this is the same idea, and I'll go to the conclusion because I'm almost out of time. So I've presented a first work in trying to understand whether neural nets can learn very simple reasoning tasks and what are the limits of our understanding of generalization. There's many more work to do there. This is just like a framework where we'd like to do more experiment and find in which cases you can actually reach some kind of reasoning through very simple examples that you can control clearly. So there's many more work to do here. I'm done with this presentation, and thanks again.
Thanks, Samy. By the way, we did not coordinate our color.
No, you called me this morning.
So the first question we have is, can neural networks learn to reason? I'm kidding. There was maybe we can start with a clarification question. You mentioned that memorizing is a way of generalizing.
It's helping generalize.
It's helping generalize.
Yes.
Okay, okay.
Yes.
And can you expand a bit in what sense?
So I gave an example where in order to solve the task, it's good to have remembered some of the things you've seen during the training set, precisely the things you've seen, not just like from the distribution. And that usually helps getting a solution. A paper I didn't talk about, but I mentioned in my slides, is a paper where they have a neural net and they added a nearest neighbor combining with the neural net and showed that the nearest neighbor was helping significantly to solve new test examples. And so that there are a few papers showing that.
Yeah, thank you. Then there was an interesting question about basically a human baseline. So it was about the block pointer task. If we give the block pointer task to humans without, with holdout shift, without telling them the rule, would you expect humans to be able to generalize?
Yeah, I've got that question many times. I think for the visual task, yes, because we're completely brainwashed with images, and we would actually maybe not even realize that we haven't seen part of the distribution. So humans would solve it. But for non-visual tasks, like just number ones, it's possible, or even something that has no like relationship with tasks that we're used to, then humans would do fairly bad on that. Yes.
And continuing in the human direction, there were a couple of questions, but I'm going to group them together, which were basically aiming at where do you see this line of work on the more general trajectory to something like consciousness or creativity, and related to that, there was a question about causality. How does that fit into your vision of generalization?
I think for me, I mean, the question of causality is, I think, humans are maybe machines that can reason with causal mechanism should need much less training examples to solve the task that they have at hand, because they only look at causal relationship, and so you need much less examples to actually solve it. And so that relates to some of the experiments where we see that we actually need a huge number of training examples to actually solve the task. But if the machine had a more causal understanding of the world, it would understanding much faster, so with less training examples. I don't know about consciousness, though.
Okay. So then let's leave it there.
Yes.
Thanks, Samy, again. Thank you.
Okay, thanks.